Welcome to video 1 of lesson 4.1, Graphing Quadratic Functions in Standard Form. So obviously the objective for today is that you be able to graph quadratic equations in standard form, which is y equals ax squared plus bx plus c. Okay, so a quadratic function is a function that can be written in the standard form, y equals ax squared plus bx plus c, where a is not equal to 0. Otherwise, you don't have a quadratic, you have a linear function, because you would just have something in the form bx plus c. So that would make it linear. The graph of a quadratic function, however, is a parabola. The parent function for quadratics is the function f of x equals x squared. The graph is shown below. You can see it's a nice little curve. Y'all should be familiar with parabolas from your prior math courses. The lowest point on a parabola is the vertex. It could also be the highest point. In this case, it's the lowest. The vertex for f of x equals x squared is 0, 0. You can see there the graph passes through 0, 0 and then turns. The axis of symmetry divides the parabola into mirror images and passes through the vertex. So in this case, it is the line x equals 0. That is the equation for the y-axis. So the vertex lies on the y-axis, which means the axis of symmetry is x equals 0, because that is actually the equation for the y-axis. Okay, so we're going to graph y equals 2x squared, and then we're going to compare that graph with the graph of y equals x squared. Now, one thing I do want you to do, even before you start analyzing, before you start your table, is to go ahead and draw y equals x squared on the coordinate plane that you are going to use for y equals 2x squared. Anytime you're asked to compare a graph with a parent function, always just draw a quick sketch of the parent function. It'll make the comparison a lot easier. Then you go ahead and you make a table of values for y equals 2x squared. So pick some convenient x values. In this case, picking -2, -1, 0, 1, and 2 works. That'll work most of the time. If you have a fraction there in front of your x squared, you might want to pick values that'll work well with that fraction, but we don't. We have a 2, so we'll stick with -2, -1, 0, 1, and 2. So we pick the x values. The y values are generated by the function itself. So you can see right there in this table, it's got the y values filled in, but the way that those y values were generated was by plugging in the x values. So for instance, for x equals -2, you plug -2 in for x, and you have y equals 2 times -2 squared. -2 squared is 4, because -2 times -2 is 4, times 2 is 8, and so on. And that's how we got the y values. You have to generate those from the function. Okay, so then you're going to plot the points on the table and fill in with a smooth curve, and you will get your picture of y equals 2x squared. So you can see it fits right inside y equals x squared there. So they have a lot in common. So when we're comparing them, they both open up and have the same vertex and axis of symmetry. Let's go back to that slide. You can see here that the vertex is 0, 0 for both of them. So that means the axis of symmetry is the line x equals 0. They both open up, so we can see that those are the similarities. So what's the difference? Well, multiplying by 2 makes the parabola y equals 2x squared much more narrow than y equals x squared. Okay, and honestly, I like saying more narrow, but the proper grammar is narrower, but that just sounds awkward. But anyway, that is the correct way to say it. So the graph of y equals 2x squared is narrower than the graph of y equals x squared. All right, so now we're going to graph y equals -1/2 x squared plus 3, and we're going to compare with the graph of y equals x squared. Okay, so we're told to compare with the parent function, so the first thing you do is draw a picture of that parent function. So go ahead and sketch y equals x squared on that little coordinate plane provided. Okay. All right, now let's make a table. Now, again, we get to pick our x values, but I'm looking at after I square my x values, I'm going to be multiplying by -1/2. And it's just a lot easier to multiply even numbers by a half than it is odd numbers, because if you have an odd number, you're going to end up with a fraction. If you have an even number, you're going to end up with an integer after you multiply. So I'm going to pick just even values for x. Okay, so instead of going with -2, -1, 0, 1, 2, because the ones positive and negative are odd, I'm going to do -4, -2, 0, 2, and 4 for my x values. Okay, now again, the y values are generated from the equation, from the function. So when I square -4, I get +16 times -1/2 gives me -8 plus 3 is -5. And I just keep going from there. -2 squared is +4 times -1/2 is -2 plus 3 is 1. And you just keep going from there. Right? Once you have that to that coordinate plane that already has the y equals x squared, go ahead and plot these points from the table and draw a smooth curve through the points. Okay, so this time our graph looks quite a bit different than our original graph. Okay, both graphs have the same axis of symmetry. See, they both do. They both have the axis of symmetry still at x equals 0. However, the graph of y equals -1/2 x squared plus 3 opens down, okay, and it's wider than the graph of y equals x squared. Also, its vertex, you can see right here, here's the vertex. It's actually a maximum point on this one, or contains it's a point where you have the maximum function value. It's actually 3.3 units higher than the vertex of y equals x squared. Y equals x squared has its vertex at 0, 0. Y equals -1/2 x squared plus 3 has its vertex at 0, 3. Okay, some properties of the graph of y equals ax squared plus bx plus c. Their characteristics include that the graph opens up if a is greater than 0 and it opens down if a is less than 0. An upward opening parabola looks kind of like a smiley face, so if a is positive, the whole thing is positive and it's smiling at you. A downward opening parabola kind of looks like a frown, so if a is negative, the whole thing is negative and it's frowning at you. Kind of a silly thing, but it will help you remember because you're going to need to know all these things. Okay, you're going to need to know how to analyze the graphs. The graph is narrower than the graph of y equals x squared if the absolute value of a is greater than 1, and wider if the absolute value of a is less than 1. And that's a lot like the absolute value functions that we've looked at before. Now, you need to know this, that the axis of symmetry is at -b/2a, and the vertex has x-coordinate -b/2a. This is an important thing for you to know. You need to be able to analyze quadratics from here on out. So you are going to need to know that. That's not going to be a formula that's given to you. The y-intercept is the point 0c. Why is it 0c? Well, if you plug in 0 for your x's, you end up with y equals a times 0 plus b times 0 plus c, and so you just end up with y equals c. Okay, our last example for this video is to graph y equals 2x squared minus 8x plus 6. Now, we want to start with the vertex because the axis of symmetry goes through the vertex, and you're going to want to utilize that axis of symmetry. So the first thing we do is we find the vertex. In order to do that, you identify a, b, and c. Okay, so the coefficients are a equals 2, b equals -8, and c equals 6. And it's always good here to just get an overall picture of what's going on. So, and you can do that by looking and going, okay, is a positive or negative? A is 2, so it's positive, it's greater than 0. So since a is positive, the whole function is, and so the parabola is smiling at you. It opens up. So that gives you a mental picture of what's going on. Step 2 is to find the vertex. Now, we were just given a formula for the x-coordinate, and then we'll talk about what to do to figure out the y-coordinate. X is negative b/2a. So we have negative, and then b is -8. So we've got the negative on the outside and then -8 in the numerator. over 2 times a is equal to 2. So we have negative 8 over 4, negative 8 over 4 is negative 2, and then negative 2 is positive 2. So x equals 2 is the x coordinate of our vertex. Now to get the y coordinate, you take the 2 and you plug it into the equation that you have for your function. Well, that makes sense. That's how we found the y values when we were graphing in examples 1 and 2. So that's what we do here, but we're just doing it for the vertex in particular. So we're going to find the y coordinate of the vertex by plugging in 2 for x. So we get y equals 2 times 2 squared minus 8 times 2 plus 6. So let's see. 2 squared is 4 times 2 is 8. Minus 16 gives us negative 8. Plus 6 is negative 2. So our vertex is at 2, negative 2. So you go and you plot that point. So go ahead and plot that point right now. And go ahead and label negative 2, label 2, negative 2 on your graph. Okay, this particular example doesn't ask you to label the vertex and the axis of symmetry, but the problems like this that you'll see on your rounds will. So go ahead and plot the point 2, negative 2, and go ahead and label it. Then draw the axis of symmetry, x equals 2. Now, you'll see on the slide here, the book does it with the solid line. I use a broken line for it, so I would prefer that you do that. It's not a huge deal, but that way I know it is not actually part of the parabola. It's not actually part of y equals 2x squared minus 8x plus 6, but it's something related to it that's important. So we're actually going to use the fact that it is an axis of symmetry. It's the line where you have mirror images across it. Okay, so we're going to identify the y-intercept 0c, which is the point 0,6 because C is 6. You plot the point 0,6. Okay, when you plot the point 0,6, if you notice, it is 2 units to the left of the axis of symmetry. So what that means is across that axis of symmetry, you're going to have another point that's the same distance from the axis of symmetry. So you're going to go 2 units to the right at the same height at y equals 6 and plot a point at 4, 6. Okay, that's using the symmetry. It helps us out a lot. So here we've got the vertex and then the axis of symmetry on there. Again, I use a dotted line for that. And then you're going to plot the point 0, 6. So 1, 2, 3, 4, 5, 6. So right there, 0, 6. And then you're going to reflect to the other side of the axis of symmetry till you're 2 units on the other side. You're going to plot a point at 4, 6. Now, really, you need another pair. You need 5 points to draw a parabola really well. We've got 3. So what we're going to do is we're going to evaluate the function for another value of x. Well, let's see. We haven't used x equals 1 yet, and that's a very convenient value to use. So we're going to use x equals 1. All right, so we need a y value. How are we going to get a y value? The same way we've been doing it. We're going to plug in x equals 1 and generate a y value. So y is going to be 2 times 1 squared minus 8 times 1 plus 6. And let's see, that gives us 2 minus 8 is negative 6 plus 6 is 0. So we're going to plot the point 1, 0. And its reflection, so let's see, 1, 0 is right here. It's 1 unit to the left of our axis of symmetry. So we're going to reflect across the axis of symmetry to 1 unit to the right. And that'll give us the point 3, 0. All right, so you can see here we've got our 0, 6 and the reflected point 4, 6. Here we've got our point 1, 0 and its reflection 3, 0. And now we can draw in our nice parabola. Now on this one we weren't asked to compare it with y equals x squared. When you're not asked to make the comparison, you don't have to draw the parent function. So you don't have to draw the parent function and you certainly don't have to actually write out the comparison. Okay guys, that is it for video 1. Meet me back here in just a second for video 2 and we will talk about maximum and minimum values.